단순한場所は、場所は、僕はあっちの方なんだけど、ここもどうせ空いてるから。でも、いや、多くはないか。
will give this opportunity to talk here. And so actually, last week I got cold, and now I'm basically recovered, but my voice haven't returned yet. And yeah, I'm sorry for this bad condition. But, I mean, I would say my voice is too loud. Maybe this bad condition gave the appropriate volume. And so, yeah, the table of this talk is about one example of a graph called the simple graph of type D2. And the main result is that we can prove the derived equivalence for this graph. And in the first section, I will explain what is this graph. And this talk is over complex number field. And first, the variety we consider is the 5-dimensional quadratic units, of course. And yeah, now in this talk we basically study this dimensional quadratic, but we will also consider the 6-dimensional quadratic. And now it is known that this 6-dimensional quadratic is isomorphic to the orthogonal Grassmannian of for 8. But you know this orthogonal Grassmannian for 8 has 2 connected components, and each 2 connected component is isomorphic to Q6. I describe those 2 connected by using plus or minus, and now Q6 is isomorphic to 1 of them. And because this is Grassmannian for 8, it admits bundle S, so which is on Q6, which is a plug for the universal bundle of this orthogonal Grassmannian. And in the world of quadratic, this bundle is called a spinor bundle. Actually, so this quadratic has 2 different spinor bundle depending on these 2 connected components. So spinor bundle means one of the spinor bundle. And this money. And the important thing to us is that the first chunk of this rank 4 bundle is minus. And it is also known by observability. If you restrict this bundle to Q5, it gives the spinor bundle. In dimensional quadratic admits a unique spinor. And the restriction of S gives the spinor bundle of Q5. And the general section of one of the spinor is non-degenerate. Which means the comparator of this section is rank 3 non-degenerate. And this 3 bundle, of course, have many isomorphism class depending on the choice of the section here. And they are called the Ottaviani bundle. And it is known by Ottaviani that the moduli of Ottaviani and using the choice of this section, you can embed this to the projective representation of the global section. So this gives the bundle, and now this is isomorphic to T7, and under this embedding, this modular space is isomorphic to the complement 6-dimensional quadratic. And so for this 8-dimensional representation, this is an 8-dimensional representation. The spin group of degree 7, and this also acts on 5-fold, and by this action, the 4-fold is a homogeneous space of this algebraic group, and it's isomorphic to 7 over the parabolic corresponding to the root alpha 1, and the alpha 1 is, so this is algebraic group of type B3, and alpha 1 is here. And this question, so of course, I mean, because this atom here, so there exists a map, the homomorphism from spin to the homomorphism of dimensional factoring, and it is known by the structure here is transitive. So what I want to say here is the Ottaviani bundle is not unique. So there are many isomorphism graphs. It's unique up to the action of the automorphism group. And now, so it is known by Kanevitz.
The automorphism group of 5-dimensional quadratic, right?
Yes. Also now,
Automorphism of the quadratic is the orthogonal.
also, yes. I think so. And yeah, I think so. This group, this map gives, I mean, one frames, right? I don't know the conceptual. I don't remember the correct statement. There's something similar to the ball. And it is known by Kanevitz that if you consider projectivization, which is denoted by W, so this is the projectivization of some of the Ottaviani bundle. But I mean, as I said, the action of the automorphism group is transitive. So this projectivization is unique as an abstract one. So if you also regard the projection, I mean, you have many isomorphism groups, but as an abstract, this is uniquely determined. And I mean, the projectivization here, there's I mean, some ambiguity for the definition of the projectivization. And today I employ the definition in Hartman's book. So this is the projectivization. Should be recognized with this G. And now, so you say this projection is P, and if you consider the linear system responding to the this projectivization, and this is because I mean this the division of this global section is equal to the global section of this bundle G, and this has the 8-dimensional global section, so 8 minus 1 gives 7, and because I took the projectivization, so this is isomorphic. And the image is
Who is here on one? Who is
yeah. It's a bit of a yeah. Again, your people are and actually under this project, and now we have two products. So say the first one is Q plus, and the second one is Q minus, and I mean by this projectivization, this is isomorphic to the projectivization of some Ottaviani bundle on this another quadratic part. So, so we found two-bit bundle structure of this W, and this variety limits two different Pn bundle structure for the same n. So it's called the. So in that sense, I mean, we say something we can do. For the truth, so we consider two varieties. First one is the total space. The first five-dimensional quantity, and the law is this one, the dual of Ottaviani bundle minus one. For this total space, I employ the dual notation. So this is now the spectrum of the symmetric algebra of G1, the dual of this one. And the other one is the corresponding total space for the other 5 points. And so this is G minus 0 minus 1. And because they are the total space, so we have two canonical closed subvarieties. They are the section. Yeah, they have, I mean, dimension 8. And, you know, so they are H4. And if you compute the first chunk as here, and as I denote in here, the first chunk class of this one is equal to 2. And this is first chunk class 0, so this also has first chunk class 2. And because I twisted that by minus 1, this has the first chunk class minus 5, and which is equal to the first chunk class of the canonical bundle of the canonical chord, so which means this is local Canadian. Okay, so now because we have two varieties, so we want to growing up along those varieties. So this is a daily business, and now I mean from this construction, so it's like moving to the space here, and the bundle is the exterior tensor product of 2 O minus 1 of each probability, and this is too long. So today this will be denoted by OW minus 1 minus 1, and it's also isomorphic to the following minus. Yeah, this is information. And if you consider the section here is E, and this E, their section for this space is equal to the extra dimensions for these two blowups, and this is of isomorphic to W, and other these projections. I mean, because this is the exceptional divisor, we have two projections into them sections, and this recovers the sorts of the loop. And because I mean, we know these two are birational to each other by this go up and one go down. And so now we have this bilateral map. And if you consider the optimization of these two varieties, then these two are cropping contractions, and this bilateral map is the simple crop. It's called the simple crop. Of type theta. So this is a shin and what is called D2, because so now we consider this root W, and for this root W, there is a distance action in the simply the algebraic group of linking type G2. The action, the thing is that this action, this is homogeneous. And I mean, if variety admits two different p-n bundle structure, such structure gives a strong restriction to the geometry of the variety, and in many cases, is a rational homogeneous variety. And now, this W is the only known case. It is the only known example of this is not rational homogeneous. And it makes this example more sometimes change example. Go. Alright, besides that, that is only known example of non-homogeneous solution. And this example, this book is also has relation to K3 degree. Because I mean, if you take a general section, this body, and consider its zero section, then I mean, zero reference, then it gives a K3 sample of degree 12. And such class of K3 sequence is first studied by the and then by Fawcett, so Ray, and then so Miura, Okawa, Ueda, and after that, and the words. What I mean is this, so K3 surfaces are already studied by the geometry. Choose general section. And we said that today is was announced the conjecture by Honda and all of the holes scale is so which means they use equivalence of x plus the category of x minus. And this is that's our linear so triangulated categories. And another thing I can blame is that under this equivalence. So trivial bundle goes to the trivial bundle. And just 1 week after we announced this thing, so it was also announced by him. I don't know how to pronounce, but so he also derived equivalence using another. So he used the semi-oscillator decomposition of this common blowing up and used the mutation method to prove this derived equivalence. So I mean the equivalence he constructed is a kind of more complicated to mine. For example, I mean it's unclear what is the image of the trivial bundle. And in that sense, I mean my equivalence is found no compatibility with structure. And strategy to prove this derived equivalence is the one using tilting bundle. So first, I briefly recall what is the tilting bundle. To say the x is the projective scheme over some nice R. And then we say check is tilting. And the following conditions are some. We assume extension of T is shared for all non-zero R. And sometimes this property is called pre-tilting property. And the other condition we assume is that the current of the bundle taking the derivative with T. Now we consider this in the unbounded category. Because of the plan C. Unbounded category. Yeah, also conversion. And the color is important. And this condition is called the generating property. So here the tilting is pre-tilting plus generator. And if there exists a tilting, the important property of the tilting is that taking the drag with T, so now gives the drag equivalence. We are cutting fifth. And the drag category of like finally generated drag modules for that in the whole machine. And then over one. First one makes exception, and now any fullness corresponds to the generator T, and the strong exceptional property corresponds to the relative. And because we study computational property, consider the Derived category. So this is the category of conjunct seeds of the. And now by capital, so it is known that this drug category, the fruit exception operation consists of 9 nodes plus a spinal. Today I don't use this exception correction, but instead I use these two to the other side of the exception correction. And in this talk I consider the exception correction starting from O minus 2, O minus 1, and then F, O1, O2. And if you consider the direct sum of S and line bundles, where A runs from -2 to 2, then this is a tilting bundle on this configuration boundary. And for that, X, so X minus. So now to natural projections. The question is, X plus what X inputs? Wow. And the answer is let's clear that. Clear. This is a generator. So when we compute the extension, then we are having to take the tilting property. We have to consider any, non-zero degree set of extensions. Now we consider bound. It's clear that all negative extensions vanishes. So now I consider the sum of all positive set of extensions. Then, the vanishing function is given by x of the of O2 and the of the spiral. And this is too long, so not today. I denote this by W2. Oh, sorry. Sorry. This is the definition. So let's log this extra file. And then this non-vanishing extension actually has one dimensional. And this is basically from the Wahei computation. Exactly. As you know, this for extension is as the sum of the extension in quadratic quadrupole of O2. So S tensor with symmetric power, K symmetric power. K here is K here of the Wahei bundle divided by 2. And point is that this bundle here is not irreducible homogeneous. which means we cannot apply the variable Bayes theorem directly. Now, because I mean, we have an exact sequence like this. So I mean, definition, we are within this exact sequence. Then taking the symmetry of this exact sequence, so we can inductively compute this cohomology using a variable Bayes theorem. And so you can actually this is a variable Bayes theorem for type D group. So it's stated that usual plus minus. Anyway, and corresponding to this one-dimensional non-vanishing extension, so there exists a unique, so non-trivial extension of 2 by this Kuban of the spinner. And I define the bundle P as the bundle which fits in this unique non-trivial extension. And then usual and semi-universal extension only reveals if you consider P on the side of x plus or x minus, so choose the signature and then taking sum of 5 line bundles plus this extra bundle P, which was replaced with by this spinner bundle, and now this is the tilting bundle on x plus or x minus respectively. And the train, so I mean the proof is that the endpoint link of P prime on the side of x plus is moving to the endpoint link of P minus on the side of x minus. That's how I do it. Remember that R is a limitation. This is the singularity. And of course, I mean, once you know this mobile algebra, because I mean, we have the direct equivalence tilting bundle by composing these two tilting bundles. And I mean, the target gives the by dot gray. So now the basic property of the tilting reveals and the term. Actually, this is a formula. It's easy to compare line bundles. So this is since it's the signature of the line bundle. It's easy to compare the tilting bundle. And this is compare. Sorry. And this is compare the link by P. I mean, I think it's easy to compare line bundles, but it's a bit difficult to compare real line bundles. So, what do you think about both? Fine. So I mean, of course, I mean, by taking line bundles, so you can move bundle. Now I am right. But if you consider original, I mean, exceptional connection, you also have an extension from here to here and here to here. Then we already have some extension from here to here. So more negative thing gives more complicated homologies. So I try to avoid such complicated things. So that's why I moved them, I mean, to the answer.
So do you think that compare the biological factor?
So I mean, I tried that first, and any relationship between, I mean, tautological bundles, scalar bundles. But I mean, I will explain these, I mean, bundles P plus and P minus are related by natural geometry of this group. And the key observation for proving claim A is that the map from X plus minus to spec R is grouping contraction. And which means this is isomorphic in codimension 1. I mean, isomorphic outside codimension 2 roots. And which basically shows that the pushing force by this probing contraction gives an equivalence between the category of reflexive shifts to X minus to the category of reflexive motions over this normal ring up. And now T minus lives in here because it's a random. And now this equivalence, well, I mean, actually we don't need the flopping contraction property for this claim, but I mean, today for simplicity, I say this is because of the flopping contraction, but anyway, the consequence is that this endomorphism ring is isomorphic to the endomorphism ring over R of the push forward of using one. And now, because we have this isomorphism, so it is enough to show the following claim. The claim B is that, so the push forward of T plus by X plus is isomorphic to X minus push forward P minus as an R module. And as I said, so it's easy to see because this is a float. The push forward of OA on X plus is isomorphic to the push forward of O minus A on the side of X minus. This is standard. The point is that the difficult part is that the compare of the push forward of P plus and P minus. And this is a bit difficult because I mean, so P plus minus are defined using some crazy extension. And now, I mean, at this moment, we cannot see any natural geometry on the bundle P plus or P minus. But so from now, I explained they have natural geometry. And for that, now consider the homogeneous variety of type D4 and mark these two vertices. Then it gives a loop. So in this Boltzmann Grassmannian 3A, it has become rank 2, and it has like repeatedly bundle structures. In each connected component. This is what I'm going to as I said. So this dog, so Boltzmann Grassmannian 4A have two connected components. And they are both naturally dominated by Boltzmann Grassmannian 3A. And as I said, they are both isomorphic to six-dimensional quadrant. In 6 and 9. Dimensional boundary. This six-dimensional boundary. And now we are considering the and second. So B is a rank 3 universal from Grassmannian 3A, and say S plus minus B rank 4 universal subbundle on Grassmannian 4A. And then it is known that this three-bundle structure is given by projectivization of this universal subbundle presented by 1. And this is an important notation of the projectation. And we saw there exists surjection from S dual. On quadratic manifold, this is isomorphic to the one-weighted spinor bundle, and our Ottaviani bundle is surjected from this spinor. And this one is a projectivization, this bundle on quadratic 6. And now this one is a projectivization of this one bundle on quadratic 5. Anyway, there exists a natural image. And everything commute. And now, Grassmannian 3A, and the input to projection by P and Q, and by abuse of notation, we also denote these projectivizations by P and Q. And commutativity justifies that abuse of notation. And now there exists a tautological sequence. So started from P, and now fullback of the spinor bundle, tautological bundle on Grassmannian 4A. And then, so if you, this has rank 3 and this has rank 4. And if you compute the first term class, so you see the co-kernel is O minus 1, 1. And this is tautological sequence. But we have another tautological sequence by using alpha projection. And so you can embed this to the fullback of S minus. And then the co-kernel is this one. And now you can take the push forward, push out of this diagram. And now there exists. So you can complete this exact sequence by taking some push forward, push out. And Now we have the same program. Let's make more any functional algebra statement you write. And this construction two exact things. This is so say this one and this one is and this one is minus. And now you see this exact sequence is very similar to the extension we took in the construction of the derivative. So we took some going up, so which was given by total space of O W minus 1 minus 1. And of course, this is projected to W and so this diagram exists on the orthogonal minus. Now I mean we left everything to using that notation. So now I mean so we are working with this diagram. This is pi and this is pi plus and this is pi minus. And now, so three sequences, this one and this one, to exchange that by using this projection. So like that sequence comes. So back, so back and this is the spin button. And back E and O minus 1 0. And now this is actually we cancelled with 2 0. Because so remember that. So in here in the distance. So this one is the normal one though, I mean one of them and one remember. And because of that, this OE is isomorphic to O minus 1 O minus 1. This looks a bit strange because I mean this is effective but this is negative, but it's possible because this is not conjective by. And now this is an exact sequence on X tilde, but you can push forward this to X. And now it gives this is a sequence. Go. It is smooth by using standard exact sequence. Check that push forward is just a program. And this two shows this two small that by projecting just one. And this exact sequence is actually not split. And we can do that. And because of the uniqueness of the extension, so we can conclude this push forward is actually a small bit to and now the speed argument shows the corresponding statement minus side. And that's what we wanted to compute is X plus push forward T plus. Now it has more X plus push forward we push forward by pull back E. But now, commutativity, now I will push forward in here. And now by the commutativity, so this is canonically isomorphic to this one. I replace this one with this one by using the commutativity of the eigenvectors. And now, so using the side of minus, so we can conclude that this one. This is the one. So now I claim this also proved, and now the proof of 7 is complete. And so this is proof. And what I want to say is, so if you consider some space of a vector bundle which is Caribbean, if you want to construct some tilting bundle by putting back tilting bundle on the base, you may need non-trivial extension. And in my feeling is that, in many cases, found that such extension has a natural geometric interpretation from the geometry of the roof. So this is what I want to share. This is the idea. We may have some non-trivial extension, we consider some polar space, but the extension comes from the geometry of the roof space. But not. And in the last 1 minute, I will talk about another example of simple growth. So remember that the simple growth today is called all type G to that. And of course, there are more examples. I don't know. That's funny. I just borrowed his notation. Yeah, I don't know what is that. G2 means that they exist action from G2. Yeah, I don't know what is. Other than so 2, 3, 4, 5, 6, 7, 8 classes found by unit. Is for AN cross AN. This is just a sample, or sometimes also called the field block. And the class is called AN. This is the type. And we have one more type A, which is called AMG. And so for the block, so we basically use this kind of marking. But for AG, so we use the middle one. This is AG and AN. And they exist, or there also exists a type C, but now the rank of the root system is 3/2 and -1. And where so n is even, and at the end, and F4, G2, and G2. So this is this is a classification of the simple group. Simple group is a group which is connected by one smooth blow up and one smooth blow down. And if you consider such group, there exists a group as an external. And it's possible to kind of partially classify groups. And because groups are not completely cut. And for these known classes of simple groups, random equivalence for standard graph is also standard graph. And for Mukai graph, this is proved by Sensei. And the difference for any case is n is equal to 4 by 1 with the bottom here. And think any, higher degrees are, and for C case, so n is equal to 2 transformed by 0. And I think other cases are open. And n is equal to 4 but proved by T. So he also proved the case of D to the same time as B. And n equal 5 case was worked by so Marco and K. And I think higher rank cases are open. And F case is also totally open. And in the case was first proved by and this other case, today I proved, and at the same time as me, so he also proved using another method. He didn't construct any tilting part. And the existence of tilting is, for these cases, the existence of tilting bundle depends on the structure, the choice of the rotor. And for the linear model like today, it's quite easy to construct tilting bundles. Or well, means so if you talk about the isomorphism of so basically we take the formal neighborhood of the grouping groups. But today I took some variety, and such choice of variety is of course not canonical in that sense. And for this case, very recently in in my joint work with Donovan and about so we constructed a tilting. And this is still in progress, and now we are trying to prove the existence of tilting bundle for arbitrary cases, and we are also trying to prove the direct equivalence for arbitrary cases for the G. And for n is equal to 2, so this is, for type C, this is known by Edo. And I also constructed a tilting bundle. And for type D, the existence of tilting bundle is totally open. Now I'm trying to prove the case of n is equal to 4 and n is equal to 5. So please do not try to this before me. Yeah, F4 case is also open. So F4 case, I'm sorry, I don't have time, but you want to say in F4 case, the linking diagram is like this, and the marking is this one.
Marking is about using polyps.
Yeah. This is of F4 group. Yeah. So and for these two, markings, there exists a corresponding homogeneous variety of equivalent one, and for those homogeneous varieties, the existence of a cross-strung exceptional collection or tilting bundle is still open, even for homogeneous varieties. So in my feeling, it's quite hard to construct such tilting bundles, and also it's quite hard to construct tilting bundle for the corresponding curves of the plot. And for G2 case, I constructed a tilting bundle. And of course, today I constructed a tilting bundle of G2 data. And yeah, finally, I want to say there may have, other examples and simple flops or loops. And I think the limits are completely crushed by the case of homogeneous. So if you find the extra example that is homogeneous loop, and like this case, and such example is also will be super important in the world of Fano variety. Related to the classification, characterization of rational homogeneous, like Kappa. That was the same. Yeah, that's all.
Okay, any questions or comments?
I ask you a question. The security is the given by control.
Yeah, that's what I don't know yet. So the natural candidate of the Freedom kernel is a problem over this singularity. I don't know if that Freedom kernel actually gives the equivalence. And I don't think the equivalence I constructed is not that one. I think in my feeling. Yeah, because in terms of Freedom kernel, so I constructed the Freedom kernel for the case n is equal to 2, so Freedom kernel. And of course, for these cases, Freedom kernels are known, but for any other cases, Freedom kernels are not known except this case. So in this case, I proved that actually fiber product, the structure single of the fiber product gives the Derived equivalence. But the tilting bundle I used for that time was more or less symmetric. So today I used the exceptional collection, which looks a kind of symmetry. But yeah, that's what I mean. So it was another tilting bundle. So I believe two statements. So one is that the structure signal of the fiber product gives a derived equivalence for this case. And the second statement I believe is that we can realize that derived equivalence using tilting. But that tilting bundle will not be the one I constructed today.
Any other questions or comments?
Does your theorem imply the equivalence of the case-free surfaces?
So using planar periodicity business, so I can also produce the derived equivalence of cases. The derived equivalence was already deeply studied by Kapska and Rampis using the Rampis theory. So they have one more stronger result, I think.
Another question is, can you compute the flop autoequivalence?
Taking the dual of the derived equivalence. So by composing these two derived equivalences, I can construct derived autoequivalence, which fixes the Lagrange bundle. And I believe that will be a kind of spherical quest. Maybe the composition, I don't know yet. Yeah.
Questions or comments? Let's start again.
For announcement, everybody who is in this room should go and make photo just outside on the skate stairs. To the right of the please. Be here now. All